So after watching this video, you will become this. To that. Yay! Hello guys, I welcome all of you to my channel Physics in my way. So in this video I am going to talk about how to plot phase trajectories. So it is a very important question. So every year in GATE or say JEST or NET, even in any other exam also, this phase trajectory is important. So at least there is one questions from phase trajectories. So I am going to clear all your doubts regarding phase trajectories. So initially I will talk about what are the properties of phase trajectories and how to plot step by step. So when you are given a potential, how to plot from those I will also discuss in detail. So initially I will discuss some standard phase trajectories of some given potential. Then I will discuss some previous year questions from NET and GATE as well. So I hope all of you are going to enjoy this video. So I request all of you to be with this video till the end so that you don't miss out any important points. So I'm also leaving out a poll here. So please do vote. How are you liking this all kind of videos I'm uploading in my channel regarding interview session or any other related topics. So I'm going to upload many more topics in future very soon. So stay tuned for that. Okay, before starting the video, one request from my side. If you are new to my channel, please do subscribe here and hit the notification bell icon so that whenever I upload new videos, you will be notified first. Thank you. Okay, so this is going to be the one shot video, means all the knowledge I have gathered, all of those I will share with you. So watch this video from begin to end, then you will get to know all the related information regarding how to draw phase trajectories, and I guarantee you will become a pro. After watching this video, many more concepts will be clear, so it will be easy for you to get a question done in NET or GATE or JEST. So without wasting much time, let's start begin the video. So first of all, what is a phase space? If someone asks you, the answer is obviously, so how the momentum of a particle is changing with position, that is plotting the momentum versus position in a graph gives you the phase trajectories, and these trajectories give you ideas whether the system is conservative, non-conservative, bounded or unbounded, right? Also the area under the curve of phase trajectories gives you idea of how the time period of the particle depends on the energy of the system. Okay, so next before plotting, you need to know some properties of the phase trajectories. So number one property is, for a conservative system, phase space curve will not intersect each other. Okay, but I will also tell what is the case for a non-conservative system. So again, for a non-conservative system, so trajectories will be connected to each other, but not intersecting, but they will be connecting. So like here, if I plot, so for a conservative system, let's say if this is your phase trajectory of some system P versus Q, so as you can see, the phase trajectories are bounded. So these are all bounded and they are not intersecting each other, right? But for a case, let's say pendulum which is subject to some damped oscillation. Okay, so that means dissipative force is present in the system. So in that case, so the phase trajectories will be like dissipative. So it will like, let's say it will begin from here, and so it will be like spiral. Okay, so this is P versus Q. So as you can see, they are not cutting each other, but they are connecting each other in this manner. Okay, then the next important point is that the phase space can be bounded or unbounded. Like in this case, it is bounded, as you can see. Let's say if you have a potential of energy say this much, if you give a energy to the particle of say this level, this amount, then the particle will be bounded. But let's say if you have given the particle energy which is much more greater than this, then the system will be unbounded. So it will be something like this, or so this is just for example, it might not be correct, I will discuss later. Okay, so this is bounded and this is unbounded, that is I wanted to say. Then so there are some things that you need to keep on mind before drawing phase space curve. So what are those things? The things are, first of all, so when you have been given a potential or you have been asked to draw the phase space trajectory, first of all you need to know how to draw that potential. So you will have to have a basic idea of how to plot graph. So here is a link coming, you can click. I have also uploaded some videos regarding graph plotting, you can check that. So the potential will be given, you need to find the maximum and minimum of the points. I will show how to find the maximum and the minimum of the points. Then you need to draw energy lines on the potential curve, and the important point is, if the energy lines are intersecting, means you draw some energy line on the potential curve and the energy lines which are intersecting the V versus X curve, then P versus X curve, in that plot P will be 0 corresponding to those intersecting points. I will show how, I will elaborate how what are I'm trying to tell you. Next, if V is increasing, P will decrease. So means if the potential energy is increasing, the momentum of the particle will decrease or the kinetic energy will decrease. Okay, and if V is decreasing, then P will increase, so vice versa. And if V is constant, P will be constant, and if V is infinite, then P will have some constant value. Okay, and most important point, so some people get confused while drawing the direction on the trajectories. I will also discuss in detail. So next is drawing V versus X curve. So first of all you need to find the points Vx. Okay, so let's say you have been given a curve, let's say some Vx equal to, let's say, some minus x square by 2 and plus x to the power 4 by 4. First of all you need to find the points where Vx is 0. So if you equate Vx equal to 0, then certainly you have points. So you will have point Vx is 0 at point where Ax is plus or minus root over of 2. And then you need to do the first derivative of Vx to get the extremum points, that is maximum of the minimum of the curve. So your V dash x will be, so it is a minus x plus x cube, and if you equate this to 0, then you will find that the maximum or minimum points are at x equal to 0 or at x equal to plus or minus 1. Now you need to find the minimum or the maximum of this curve. So here is the condition for minimum, second derivative of this potential will be greater than 0, and for maximum the second derivative of the potential will be less than 0. Okay, so if you check this condition, you will certainly find that Ax equal to 0 is a point of minima and Ax equal to plus minus 1 is a point of maxima, right? So now if you draw the potential curve, so the curve will look like this. Let me erase this. So the curve will look like this. So here is the curve I am drawing. So this is Vx and this is x. Okay, so the curve will be like this way. Okay, so this is a point of minima and this is point of maxima and this is point of minima. So I have wrongly elaborated it. So this should be point for maxima. Okay, so for x equal to 0, dx will be negative, and for x equal to plus minus 1 it will be negative. So forget these arrows. Okay, or let me remove those things. Okay. Now if you calculate d2v dx2, that is second derivative, so you will certainly find that d2v dx2 is equal to, so it will be minus 1 plus 3x square. Then you will find that for d2v dx2 for x equal to 0, so it will be minus 1, so which is less than 0. That means it is a point of maxima. And if you want to find d2v dx2 at x equal to plus or minus 1, then it will be 2. So it will be 2, that is greater than 0. So it will be point of minima. So these are minimum points, plus or minus 1, this is minus root 2, this point, and this point is plus root 2, and obviously this is 0. So this point, as you can say, this is a unstable fixed point, so it is unstable fixed point. So let call it USP, and it is stable fixed point, so it is, let's SFP. So this is stable fixed point. So this plus and minus 1 are stable fixed point. If you imagine, if you keep this particle in this point, then it will be at equilibrium. But if you want to pull the particle at this point, it will come to this way or come to that way. So it is a unstable equilibrium, or it is an unstable fixed point, as you can see. You have plotted v versus x. Then I will so keeping on this concept, also basic concept of a graph also needed for plotting all these things. So now you will draw, once you plot your potential, let's say you have a potential like this, so like this is your potential, then you will draw the energy lines. Okay, so the energy lines will be here. So let me draw the energy lines. So energy line, let's say this is the energy line, let's say this is E1, another energy line, say this is E2. Okay, so I am just drawing two energy lines, many more energy lines can be there. Okay, so the important point says that if the energy lines are intersecting, V versus X graph, so the energy lines, let's say it is energy line, it is intersecting at this point and also at this point. And for this case, it is intersecting at this point and also at this point, right? So now it says if this is intersecting, then in P versus X graph, so this is P versus X graph, P will be 0 corresponding to those intersecting points. So point corresponding to those intersecting points, so this is for E1, two intersecting points are there, another is here. Okay. So this P versus X curve, this will be elliptic, this Vx is nature of x square by 2, so phase space curve will be elliptic. I will show in detail how it is elliptic. Okay, so this is a fixed phase space curve. So as you can see, these intersecting points corresponds to P equal to 0, so this point. Okay, similarly here P equal to 0, and for the E2 energy line, so the intersecting points will be something around here and here, you can draw from here. Then the curve will be like this. Okay, so as you can see, these trajectories are correspondence to two different energies. So that is why each energy corresponds to a unique trajectories. So this trajectory is also unique and this one is also unique. Okay, so this corresponds to E1, this corresponds to E2, and certainly E2 is greater than E1. Okay, and I will talk about the direction of the trajectories in upcoming slides. Okay, now another important point is if V is increasing, so if V is increasing and V is decreasing, so when V is increasing, let's say V is increasing this way, then P will decrease, so P will decrease, and if V is decreasing, let's say V is decreasing this way, then your P will increase, right? And if V is constant, then P will be constant, and if V is infinite, then your P will have some constant value. Let's understand this, how with the increase of V, P will decrease. Let's say if you have some hilly region, okay, so a ball is stuck between two hills. Okay, so here is my ball, So now as the ball let's say moving up from this point to that point, your potential energy increases, but the velocity of this ball will decrease. That means your momentum will decrease. Or when the ball is coming down along this path, so when the ball is coming down along this path, its velocity will increase and potential will decrease. So and it will go to this point, again potential energy will increase and velocity will decrease. So that means when there is maximum of potential energy, there will be a minimum of the momentum. Okay, so you can keep this analogy as this potential. Then the phase space trajectories will be like this. Okay, so as you can see, the momentum, the particle starts from here, so this point corresponding to this. Let's say now the potential energy is increasing and x also increasing, then your PAX is decreasing. Okay, and for the return journey, again P is increasing but in the opposite direction, and it goes to this point, so it is that point, and again it is coming down, so Px will increase. So the phase space trajectory will look like this. I will show you how this is becoming an ellipse in detailed calculation. Okay, now the most important thing, many students confuse, even I used to confuse, how to draw the direction in a phase space trajectories. So as a thumb rule, as you can say, so when P is positive, then the direction will be towards the positive x-axis, and if your P is negative, the direction will be towards x-axis. So I am drawing a two-dimensional plot here. So as you can see here, in the first quadrant P is positive and x is positive as well. Here P is negative, sorry, x is negative and P is positive, and here x is negative and P is negative as well, and here x is positive and P is negative. So the statement says, or the thumb rule says, as you can see, so when P is positive, let us think about this quadrant. So let's say this is a phase space trajectories and you want to draw the direction. So in this case, as P is your positive, then the direction will move towards the positive x-axis, that is in this direction. So direction will be like this way. You understand? Now what happens for the second quadrant? For the second quadrant, your Px is positive and x is negative. So it says when a P is positive, direction will be towards the positive x-axis. That means it will be in this direction, right? So as you can see, P is positive, so arrow is towards the positive x-axis. And for here as you can see, P is negative, so the direction will move towards the negative axis, so in this way, so it is towards the negative x-axis, right? And you can draw for this quadrant. So yeah, rightly you have guessed, so if P is negative, so it will move towards the, so obviously you need to keep on mind in a bound phase space trajectories, the direction will be consistent. Okay, and it also satisfies that thing. So I hope you have clear your knowledge about drawing the direction in a phase space trajectories. So next let me discuss with some example. Let's say you have given a potential like V equal to half of x square. Then you will find point for x equal to 0 and Vx equal to 0. So here x equal to 0, Vx is 0, and for first derivative of Vx equal to 0 and x equal to 0, and it will be point of minima, and the curve will be look like this. So your V versus let me remove this line. Okay, it is not removing. Okay, let me draw first V versus x, then I will show how you can plot the phase space trajectories. So as you can see here, yeah, so first you need to plot your V versus x. So it is your V versus x, right? So V and x. So it is a simple harmonic oscillator case, so the potential will be looking like this, and as you can see, it is a point of stable equilibrium, and along the stable equilibrium, tell me one thing, that these curves will be bounded and it will be more like ellipse. And if you want to write the Hamiltonian of the particle, as you can see, it will be px square by 2m and half of vx square, and it is equal to E and E is constant, and it is a conservative system. So for conservative system there will be no time dependent part in the Hamiltonian, so it is a conservative system, and obviously the curves will be bounded. Now let me draw these phase space trajectories which will be elliptical. So let me draw here. So this is your px and this is your x. So if you want to draw corresponding to this point, okay, let's say my energy line is here, then your curve will be looking like this. So it will be symmetrical. I have distorted this thing, and the direction will be this way. You just apply those rule of direction. So as you can see, when energy line is intersecting a point on Vx, corresponding to that point Px will be 0, right? If you take another energy line here, so corresponding to this point and this point in the phase space trajectories, it will be like this, okay, and you draw the direction. So easy, as you can see, it is a very easy example and known example, as you can see, and I am going to deeper and many more potential, and looking at the potential you cannot actually plot, or you cannot say that it will be a ellipse. That I will show how to take care of all those things. So now say if you have given a pendulum and which is oscillating in water, right? So actually this question have been asked in JNCSR 2020 interview. I have discussed one video. If you haven't watched the video, then please click on this I button. I will drop the link there. So let us study the system. So the here is a pendulum. So as you can see, it is underwater and it is oscillating. Let's say it starts its motion from this point and reaches this point. Then it will come back to this point, but as you can see this angle, so as you can see this angle will be less than this angle, as a viscous drag is there due to water, and obviously the Hamiltonian will be time dependent, so it is a non-conservative system. Okay, so then the particle will move towards this point like here. So amplitude again decreases and again move to this position, amplitude again more decrease, so it will gradually come to 0, say after long time. So as you can see, it is a dissipative system and non-conservative system as well. So if you want to plot phase space trajectories for this kind of system, so it will be looking like this. So let's say the particle starts from here, so it will follow a spiral path. So gradually its momentum will become 0. We never know when it is going to touch x. Okay, so initially x is 0, momentum, I give an initial momentum, then the oscillation start, so it will be looking like this. So gradually the momentum will also decrease, and next time it will further decrease, so it will decrease more and more, and then if you want to give the direction, it will be like this way. Okay, so it is a simple case of a non-conservative system. This way you can draw this kind of graphs. Okay, so some important trajectories. So a ball bouncing elastically in a conservative system. So let's say a ball is bouncing elastically. That means if the ball start bouncing from this point to that point, it will again reach that particular same height because the collision is elastic, right? So for this case, if you want to draw the phase space trajectories, okay, then it will be looking like this. So the particle starts from here. Let's say momentum is 0. So your momentum will be 0. So you can start from here. Okay. So it will be looking like this. So particle starts from here, or the reverse way you can think. Let me simplify this. Let's I have thrown up the ball. So I have given some initial momentum. So initially it's let's say it is your z axis and it is your pz. Okay. So your z is increasing at its increasing height. So and pz will decrease this way. So at maximum height, this corresponds to some maximum height h. Then again z will decrease and pz will increase, but in the opposite direction. So this will be a parabolic curve. You can also get from this Hamiltonian that it will be parabolic. If you plot that p square by 2m plus some mgz, then you will obviously find that it will be 2m into e minus mgz. So this is y square equal to 4x like curve, so it will be parabolic. So if this corresponds to certain energy, let's say correspond to let's say the curve is here, h is here, let's say, then it will be 0 when the energy is cutting this line. So if you have considered an energy line here which is corresponds to h, so let's say this h is here, then p is 0 at intersect. Now if you say let's say you have given some energy which is lying something here, and it corresponds to some another different height h dash. So corresponding to this line, the curve will be like this. Okay, so as you can see, pz is 0 where the energy line is intersecting at z value. Okay, so this will be parabolic. So this is a set of parabola for different values of energy. So if your z is variable, it is not fixed or constant, so you can draw set of parabolas. Or if z is constant, some mgh, then one curve will be there, only say this curve. Okay, so I hope you got this point. Now let us the case of some, let's say, non-conservative system where dissipative force is there. So here is a ball bouncing, but it is bouncing inelastically. So in every bounce the height of ascending will be decreasing. So this is the first height which drops. So after reaching h2 will be less than h1. So these are the order. Okay, again this will be parabola, but the thing you need to remember, so let's say the ball is thrown upward. Okay, so let's say the ball is thrown upward, so it will reach a height of say h1. So this is h1 point, then it will come down same height, so it will again come down same height with equal momentum, obviously. Okay, then it will bounce up, but for bounce up it will the direction will shift toward this, so it will start from here. Okay, so actually so this is shifting towards this, so sudden jump is there, then again it will come to ground, then again start from another velocity, so height will be more or less, and it will again reach this point. So these are the set of trajectories. Okay, so there will be sudden jump, it is coming to this point, then suddenly jump to this point, again coming to this point, then again jump to this point, and suddenly coming to this point. So obviously these lines are not intersecting, I will say, but it is connecting each other. These trajectories are connecting each other, I have already told. So this is an example of non-conservative system. So let us discuss some standard points problems here. As you can see, so a potential is given Vx equal to minus x square by 2, right? So obviously it is a inverted parabola, so I have drawn the potential like this, and this is a point of unstable fixed point. So how it is unstable fixed point? If you put a ball here, it will roll towards this or roll towards this way. So that is why it will not be stable here. So that is why it is unstable fixed point. Okay. Now if you write the Hamiltonian, it will be looking like this. So obviously it is an equation of hyperbola. So the phase space trajectories will be hyperbolic in nature. So I have drawn the phase space trajectories here and here. Now the time to put the direction. So the direction is here. As in this quadrant p is positive, so it will move towards positive x-axis. So it is this way, and obviously in this region it will be also this way. So here will be p is positive, so it will move towards positive x-axis, right? And here p is negative, so it will move towards negative x-axis. Obviously this is consistent, this direction will be same. And here as well p is negative, so it will move towards negative x-axis. Okay, so here as well. So as you can see, this direction and this direction are consistent. So in a same quadrant, the lines are close to each other, the direction must be same. So this is also important point to eliminate the choose the correct phase space trajectories. Now let us draw the separatics. Now for separatics are those lines where E equal to 0. So this is the case for E greater than 0, and this is the case for E less than 0. Okay. Now for E equal to 0, if you put on this equation, then the equation will be like straight line. So let me draw the separatics which will be straight line. So it will be like this. So it will be like, so this should be straight line. I am just drawing with my hands, and it will be straight line here as well. Okay, and this point is called the saddle point, because this line seems to intersect but it will not intersect. That is why this point is denoting it is a saddle point. These are not intersecting. Now the direction on this separatrix will be along this. As P is on positive, then the direction will be towards positive x direction, or you can say this direction will be consistent. So this direction will be consistent to each other, so all are pointing towards the positive direction. So blindfoldedly you can keep direction here, in this direction, here as well as in this direction, or here as well as in this direction. If you want to satisfy, here P is positive, so it is moving towards positive x. Here P is negative, it is moving towards negative x. So these are the phase space trajectories corresponding to this potential. I hope you got these points. So this separatic concept some of you might know, but I am again telling you to clear your concept. Okay, so I am going to discuss many more topics and many more problems. Just stay tuned. Another important point for regarding that problem, v equal to minus x square by 2. So one question asks that for the current potential, that is Vx equal to minus x square by 2, so that the particle will take infinite time to reach the unstable fixed point. That means if the particle wants to move from this way to this point, it will take asymptotically infinite time, right? So how to prove that? So first you need to write the Hamiltonian of the system. So here is the Hamiltonian of the system. Then what will be the Hamilton's equation of motion? So the first equation will be P dot equal to minus del h by del x, right? So I have taken P dot equal to, so minus del x del h by del x, so it will be P dot equal to x. So if you integrate, it will be equal to xt. For simplicity I am taking the integration constant as 0. Okay, so again your time will be P upon x. So for reaching this point, let's say this point, as you can see here ax is becoming 0, right? So here x is becoming 0, so then your t will be, so p by 0, p is also infinite, p is also tends to be 0, so it will be asymptotically tends to infinite. Okay, so in this way you can prove that the time to reach the unstable fixed point will be infinite. Okay, so the second point is so here is given Vx equal to minus x to the power 4 by 2. So as you can see, it will also be a this is also be a parabola, so in the negative axis, and obviously here x equal to 0 also a unstable fixed point. As you can see, if you put a ball here, it will move to this one or this way, then it is unstable fixed point. Then if you write the Hamiltonian, it will be like p square by 2 minus x to the power 4 by 2 equal to E. Okay, so now if you draw the phase space trajectories, now for unstable fixed point, it will be so it will be hyperbolic curve. So here the unstable fixed point, this will be hyperbola, this will also be hyperbola, and these are hyperbola. So all these energies are E greater than 0. Okay, so and for the separatrix, for about this unstable fixed point, so whenever there is unstable fixed point, there will be separatrix. So it will be a straight line like this. As you can see, for this coordinate this px is positive, that is why this arrow will move towards positive x-axis, that is this direction. So similarly here p is positive, so it is moving towards the positive x direction. Here p is negative, so it is moving towards the negative x direction. So as you can see, and this direction will be in same coordinate, will be consistent with each other. Okay, so slowly I will going to deeper some more difficult potential. Now let us look at this potential. So this is Vx equal to x to the power 4. So here then the potential curve is looking like this. So this curve will be somewhere between x square by 2 and x square by, so it will, the ellipse will be much more flatter than the previous case of x square by 2. So if you look at this point, let's draw an energy line here. So corresponding to this energy line, so it is cutting the potential at this point. So corresponding to this point, the corresponding momentum will also be 0 here, and it will also be a phase space trajectory of ellipse, but the ellipse will be much more flatter than the x square by 2. So if the ellipse is like this, then it will be much more flatter. Okay, so whenever there is stable fixed point, the phase space trajectories will be ellipse. and wherever there is unstable fixed point, then it will be more like so it will be more like hyperbola. Okay. Now here is one potential, so it is x square by 2 plus x cube by 4. So if this white line is x square by 2 plus x cube by 4, this blue line corresponds to the curve for x square by 2, and red line x cube by 4 by 4. So this white line is somewhere between x cube by 4 by 4 and x square by 2, right? So this curve will be like this. And as you can see, this x equal to 0 is also a stable fixed point, right? So it will also be an ellipse. So you no need to write the Hamiltonian and relate p with x every time. If you know it is a stable point, then it will be why it is stable point. If you put a ball here, this ball will be remain calm at this point. It will not move this side or this side. Okay. So there is no uncertainty to going this way or this way. So it will be stable here. That is it is stable equilibrium or a stable fixed point. So the curves will be like ellipse. Okay. So if I draw an energy line here, let's say this point corresponds to this point and this point. So if I draw an energy line here, then these points at this point momentum will be 0 here, and at this point momentum will be 0 as well here. Okay. So you can draw many more curves corresponding to different energy level. Okay? So for this energy level, say this curve is for this and this. So all these trajectories will be unique for unique values of energy. Okay. Now here is also interesting potential. It is overlap of x cube by 4 by 4 and minus x square by 2. So if you draw x square by 2 minus x square by 2, so it will be looking like this, and x square by 4, this will be looking like this. So this curve, this Vx will be somewhere between x square by 2 and x cube by 4 by 2. That's why it will be like this. Okay. As x cube by 4 power is much more higher, so the curve will bend towards x cube by 4 and slightly minimize the x cube by minus x square by 2 point. Okay. So the resultant Vx is like this way. So looking at the curve, you can easily tell that this x equal to 0 is a unstable fixed point, right? And this x equal to minus 1 and x equal to plus 1, these are stable fixed point, right? So you can also get v dash x equal to 0 derivative. You can get the maximum and the minimum of this potential. Then you can also easily find. So this is unstable fixed point UFP and stable fixed point SFP. So I will write this abbreviation here. So as I have told about the stable fixed point, the curves will be ellipse. So about the stable fixed point here, the curves are ellipse. Okay. And for the unstable fixed point, the curves will be, so unstable fixed point, the curves will be here. So it is unstable fixed point. So separatics will be there, and it will be much about this point. It will be like hyperbolic. Okay. So these are hyperbola, these are hyperbolic. Okay. So this is unstable fixed point. So I have put it. This should be half instead of 0. So let me write it down. So this is not 0. This is not 0. This will be greater than half, and this will be e equal to 0. And so this will be e greater than half, and this is e equal to half. How am I getting this point? These values. So this for this separatics, momentum is 0 here, this fixed point, and you put Ax equal to 0. Okay. So now for this problem, a potential is given Vx equal to minus x square by 2 plus x cube by 4 by 4. So the graph will be like this. This is a common potential. I have also shown one of my videos in graph plotting. So the potential is looking like this. Now if you put first derivative of Vx equal to 0, you will have point x equal to 0 and x equal to plus minus 1. And for x equal to plus minus 1, you will have minima, and for x equal to 0, you will have maxima. This x equal to 0 maxima is called the unstable fixed point, and this x equal to plus 1 and minus 1 are called the stable fixed point, right? So why it is unstable? If you put a ball here, I am turning it again and again. So you understand what I am wanting to tell. Okay. So now I have already told that if there is stable fixed point, then the phase trajectories will be ellipse. So about this x equal to -1, these are all ellipse, and these are the energies corresponding to E less than 0. So this is E less than 0, and for E equal to 0 we will get the separatics, right? So for separatics, E equal to 0, if you put in the Hamiltonian expression, that is h equal to p square by 2m. So if you put so get separatics at x equal to plus minus 1, p equal to 0, then it is 0, minus 1 by 2 plus 1 by 4, right? So this would be 0 by 2 and 0 by 4. That is the separatics as around x equal to 0 point. So you need to put x equal to 0 and p equal to 0. Then it will be 0. Okay. So whenever you want to find the separatics, it should be around the unstable fixed point. That is why I have put here x equal to 0 and momentum should be 0 here. So this white line, this white curve is for E equal to 0. This is the separatics. This violet curve, when the energy is slightly greater than 0, that is the energy is let's say somewhere between this. Okay. Then at this point the energy curve is intersecting the px. Then corresponding to this point, let's say this point is corresponding to that point. Then at this point this momentum will also be 0, as I have told in other examples. Now this yellow line, this is the curve corresponding to energy which is very greater than 0. Okay. And obviously it will cut the curve somewhere here and here. If this point corresponding to this point and if this point corresponding to that point, and at this point the momentum will be 0 and the curve will be looking like this. Yeah, so this is a very interesting curve. So you need to know stable and unstable fixed point, and no need to every time relate the p and x with the Hamiltonian, right? So these are the easy tricks. I hope you are getting. Now again another curve. This is just like the opposite sign of the previous one. So here bx is given as x square by 2 minus x to the power 4 by 4. Now x square by 2 curve is like this, minus x to the power 4 curve is like this. So this curve will be resultant of these two curves. And as x to the power 4 power is higher, so this whole curve will bend towards the x to the power 4 power. That is why there will be minima at x equal to 0, which is a stable fixed point here, and maxima at x equal to plus 1 and minus 1. So these are called the unstable fixed point, right? So around obviously stable fixed point, the phase trajectories will be ellipse. So around phase trajectory, these are ellipse, and this yellow line corresponds to energy E equal to 1 by 4. How I will get that? I will get by putting in the Hamiltonian expression P equal to 0 and x equal to plus 1 and minus 1, because this is separatics and this is about plus 1 and minus 1 point. So you put h equal to 0 plus 1 by 2 minus 1 by 4, then you will get 1 by 4, right? And the direction will be like this way, and here as p is positive, so it is moving towards positive x. Here also, so it is also positive x, and here p is negative, so it will move toward negative x axis. Here p is also negative because it's fourth quadrant, so it will also move towards negative x axis, right? So direction will be here, and here also. And here obviously p is positive, so it is moving towards positive x axis. Here p is negative, moving towards negative x axis, and here as well. Okay, you can see this, all the arrows are in the same quadrant, are consistent. This way, this like this is like this. Okay, and similarly here you can also put. Okay, so x equal to 0, there are ellipse. For x equal to plus 1 or minus 1, there is like hyperbola. This is one hyperbola, and this is also resultant of this. Okay, so this yellow curve is for E equal to 1 by 4. This ellipse are for E less than 1 by 4. That is if the energy line is somewhere around this. So somewhere around this. So this point and this point corresponds to, let's say, this point and this point. Then here P will be 0. Okay. Now for E greater than 1 by 4, so means E greater than 1 by 4, the line is here, somewhere here, so this is E greater than 1 by 4. So the energy is much more than the potential, so that will be unbound, so the particle going like this way. Okay. So similarly for the negative case here. Okay. negative region is also here. So whether it is moving towards this side or moving towards the positive x, the curve will be. So this is moving from the positive negative x, this is moving from the positive x, right? So these are the phase graph x square by 2 minus x to the power 4 by 4. So I hope you get it. Now I am moving to more examples. So it is a x square by 2 and x minus x cube by 3 graph. If you put v dash x equal to 0, then you will get x equal to 0 and x equal to 1 as the maximum and the minimum point. So x equal to 0 here is the minimum point and x equal to 1 is the maximum point. And for the separatrix, the energy will be, just you put in the Hamiltonian p equal to 0 and the separatrix will be around the unstable fixed point, that is x equal to plus 1. That is why I am putting plus 1 in the expression of Vx. So I have put plus 1 here, I have put in the Hamiltonian, so it will be 1 by 6, right? So when the energy of the particle will be equal to 1 by 6, so just the particle wants to reach this point just touches it, whether moving this point or whether it is coming from that region. So this curve here, let me show it. So this curve here, this curve is the separatrix, okay? This corresponds to E equal to 1 by 6. Now for E greater than 1 by 6, something the energy curve is around here, it is 1 by 6 greater than. So it is cutting at a single point on the Vx. So at this point corresponding to this point, the momentum is 0 here, and here it is not cutting, so it will be unbounded, okay? So here it is unbounded. And here x equal to plus 1, so it is unstable fixed point, there is shown a hyperbola here. And for x equal to 0, all the particles of energy is less than E equal to E less than, so the energy less than E 1 by 6, so it is E less than 1 by 6. So all these ellipse we will get. So that means the energy is somewhere between this line or this line, okay? So you got it? So whenever there is stable fixed point, we will have ellipse. Whenever there is unstable fixed point, we will have separatrix as well as hyperbola. Okay, yeah. Right. Now moving on to the next problem. So here is also a very interesting problem. If you know the graph, you can easily plot the phase-space trajectories. So it is Vx equal to 1 minus cos of x. So this have amplitude plus 2 and will have minima 0. So for x equal to odd power of pi, it will be plus 2. That is why for plus pi, plus 3 pi and minus pi, minus 3 pi, odd power of pi is the amplitude is plus 2 here. Okay. And for other even power of pi, that is 2 pi plus 4 pi minus 2 pi minus 4 pi, the energy is 0 and Vx is 0 here. So the graph is looking like this, right? Now if you want to find the derivative of this curve, dp dx equal to 0, that is x equal to plus minus n pi. That is for x equal to plus minus n pi, there is minima, there is maxima, there is minima, there is maximum. So now this point is a stable fixed point, okay? This is unstable fixed point, UFP, and this is also stable fixed point. Similarly here unstable fixed point, here stable fixed point. So I am not writing all the things. So whenever there is stable fixed point, there will be ellipse. So energy less than 2, the E equal to this yellow line. This is E less than 2. So for E less than 2 energy, this energy line are here. Then this is cutting here. This intersection point are also here. Then momentum will be 0 and it will be ellipse. Okay. Similarly for here, it will be also ellipse. For this region, it will also be ellipse, and here also. So whenever there is a stable point, there will be ellipse around that point. Now for the unstable fixed point, that is x equal to pi, x equal to 3 pi, x equal to minus pi, x equal to minus 3 pi, and so on. So these are the points here. So let me write it down. This is x equal to minus pi, and this is x equal to minus 3 pi. I have given the direction. I hope you understand the direction concept of previously. So here are the separating. This corresponds to equal to 2 energy. How I am getting equal to 2? In the expression of Hamiltonian, you just put p equal to 0, and in the expression of Vx, you just put x naught, where x naught is plus minus pi, plus minus 3 pi. So it is a odd multiple of pi, whether plus or minus, right? So then E equal to 2. So these are around the separatrix, are on the unstable fixed point. So these are unstable fixed points, so the separatics are looking like this. So if a particle have energy, it can touch this unstable fixed point, then the trajectory will be looking like this. This blue line. Now this white line, if the energy is greater than 2, that means if you have a energy line here which is greater than 2, it is not touching any unstable fixed point or the maximum of the curve, then it will not be bounded, it will be unbounded. So this curve corresponds to that E greater than 2. Okay, so these are E greater than 2. So these are the standard problem. Now I will also discuss some problems related to gate, net and jest, the previous year question. But as this video is getting elongated, it is becoming lengthy. So I will upload that previous year solution regarding phase-space trajectories in my second part. So I hope you have liked this video. So if you have liked this video, found helpful, and if you acknowledge that you have learned something from this video, your knowledge has been enhanced in phase-space trajectories, then please like my video, do subscribe here and press the notification bell icon so that every time I upload new videos you will be notified fast. So that's it. Bye bye. I will come back with the part 2 of this video very soon.